a bipod filter, and then put them in cascade, okay? One filter after another filter. Because in between, you apply voltage to current conversion many times, okay? How can we do better filtering? From this paper, you can see, this is the input. You will change to current from the resistor, and then go through the wall here, and then here, and then become a voltage, okay? So the key concept here is that M1, M3, and C2, they come up like a inductor. Okay, this is impressive, that a capacitor with an inductor, and then you have another capacitor, another inductor before you come to the resistor. So you put everything in the current domain before you become a voltage. Okay, this is good because you maintain the compression point of each node. Is not a huge requirement. You can relax them. And from this example, you can see to achieve an outband IIP3 is very, very high. So that's why this paper can achieve a sparse-free dynamic range 75 dB, okay, with a power just of 1.26 milliwatt. It's very impressive if you look at the circuit. This is already a 4-order filter, but only several transistor. Okay, you make the filter and put the signal most time in the current domain before you apply the filter. Okay, this is an important concept. But of course, this also have the limitation that why I show here is that the voltage headroom is still a problem, because for this one to happen in current domain, you still need to bias the current top and this one. The voltage you need to put here is what? This is the 1 VDS, right? This is the down connected, so it's a VGS, another VDS, and another VDS. If you put just a 1 volt or 1.2 volt, the dynamic range will not be so high. So dynamic range with this number cannot be high if you just apply 1.2 volt. Okay? So this designer applied 2.5 volt. And if you put 4 transistors, you can keep them biased correctly. 4 transistors is not a problem. At 2.5 volt, you maintain all transistors not overdrive. And then you can achieve a higher dynamic range. Okay? You increase the supply, doesn't mean you increase the power. You can see here, it's still quite reasonable load. So this has become a good concept that if you want to design very high quality filter, especially for baseband, you put the filter in current domain rather than the voltage domain. You put in filter and current domain and filter until you become very clean, you change back to voltage. Okay, this is the way that we can do there in the domain, like in the current. And for this one to happen to be put in, a high supply voltage can help a lot because you can put the device in cascade rather than cascade. Okay, and whenever you put cascade, actually is a VI conversion, IV conversion, VI conversion, IV conversion. But now here, no, it's just VI conversion at the front is linear, and then you ping to current until you become voltage. Okay, so this is completely different concept. You do not need a lot of op-amp. You cannot see the op-amp, right? I will implement 4-order with no op-amp. Okay, this is a much better filter in terms of analog baseband field circuit. Another example I want to show you is also from this year ISSCC. It's very powerful from 0 to 1 GHz band with the sigma delta ADC. The dynamic range is 74 dB with a bandwidth of 150 MHz. Okay, this is by a company, the analog device. So they actually focus on this product is extremely high performance. How can they make this possible? In the architecture, of course, you have a continuous time sigma delta load, but in between, there's a A1, A2, A3, and A4, A5. This kind of op-amp must be very, very high performance. How high? The GBW of A1 and A2 should be 80 GHz. For A3 to A6 will be 300 GHz for the GBW to achieve this kind of level of performance. How can they do this? They propose this kind of so-called nested amplifier, okay? You put a lot of GM in a less way, and then you put appropriate high-pass filter to isolate their bias. You can put this as a nested amplifier. Nested amplifier means you put a very high gain for low frequency, and very high speed for high frequency, and then you parallel them, you increase the gain, okay, from frequency to low, you use thick-oxide devices. For the gain you want at high frequency, you use the thin-oxide, and then you put them as a less design, okay? You less them. For this kind of thick line is the 2.5 volt GM, okay? For this one, also 2.5 volt GM. You also have this thin line is a 1 volt stage GM, okay? So normally, 1 volt GM is high speed. They boost your GBW. 2.5 volt is the high gain. They put the low frequency gain. So together, if you less them together with appropriate frequency compensation, you can make them a very powerful op-amp. Of course, the power is huge, but at least it's one way that you can achieve your desired performance at such a high frequency and high performance sigma delta ADC. Okay, this performance, I think, is a record performance for this kind of application. But the idea is, you want to design very good performance op-amp with this kind of level, less amplifier, combining low voltage GM and high voltage GM is also one solution. Okay. Of course, many applications of high mixed voltage design are actually on power amplifier. One example I want to show you here is that this is the simple general power amplifier. No matter what class you are working on this, maybe class A, class AB, class C, whatever. You will put a signal here to amplify here. If you put this is a 64 ohm OFDM signal like here, you need to check the output at the full swing output in time domain. Okay, what I'm showing you here is that you need to ensure that all the transistor, the voltage, the in blue color I show here, are not overdrive at all time. So you need to check in the time domain to ensure that all their voltage in terms of RMS value must be less than supply. Then you can keep this power amplifier work for you. Okay, so this is just a simple, very simple power amplifier with a higher supply voltage. If you put this one is a 3.3 volt, normally people still keep use this because sometimes you do not want another converter. You just want the supply from the battery. Okay, the battery draw all the current to this one. You improve the efficiency actually. So you increase this one just to fit to your battery, and then you design this cascade device with appropriate bias, and then you check the modulation signal that you will use. For example, your application is Wi-Fi, you check it with this modulation signal, and then see the time domain with the full power, and then you check the voltage. Is it really limited to your safe region? If yes, you keep this. If not, you need to change your bias or change your design. Okay? Of course, one important thing here is this M2. The voltage here can be very high, and the voltage here can also be very high. So you need to keep the body and the source short together. Normally, you need to short them. Okay? Otherwise, the overdrive voltage to the body will be more than the allowed one. And if you short this one, you have the penalty then, because you must use the deep end well for M2. Whenever you apply deep end well, this will be a well dial. The dial is bulky, depends on the transistor, right? You put a deep end well to circle this transistor, and the deep end well have a dial. It's a dial to the substrate that create the capacitance here. Okay. Then if you apply this as a PA, you will lose the energy. Okay. So this is some trade-off. How to protect the PA? I propose this circuit to you. It's very simple. If you apply a PA, you just put a very small transistor here. This is the thick-oxide device, it's a PMOS. The idea is that the gauge of the transistor is biased by 1.2 volt because this is a thin-oxide transistor. If the supply of this one is not yet ready, so if this is 0, this will be 0, this will be open. If this is open, the VDD will go to here. Then the transistor will be broken, right? So you must ensure that when this voltage is ready, why this is not ready? This one is not too high. So Vx must be limited to less than, for example, 1.2 volt is the limit of this one. So you put this one here. If the VDDC here, I put here, if this is a 0, this will draw the current, because this is the PMOS. So when it becomes the 1 volt or 1.2 volt here, this will be power down. Okay, so it's the automatic protection. I show you the figure, it's like here. If the VDD, this one, is high, while this one is not yet ready, this device will draw the current. Okay, you can see the orange color line. This one will draw the current, and Vx will be dropped. Okay, because of this device. When VDDC become ready, 1.2 volt here, this will become 1.2. They will shut down automatically. Then this will become open circuit, and you keep this one to operate. Okay, this is one technique that you can just protect your circuit automatically if you have two supply. Okay, you put another supply as a sensible voltage in between. If this one can be sensed, you can automatically draw the current. You keep the device not overdrive at all times. Okay. Another example. This is a millimeter wave power amplifier. As you can see, for millimeter wave design, we are talking about 30 gigahertz to 60 gigahertz, this kind of frequency. For this one is 60 gigahertz. For this high frequency, you are not really interested to use the thick-oxide guy. Okay, thick-oxide is not a good guy for you. For 60 gigahertz, all devices are thin-oxide. It's the farthest device that you can have. You put them together, you also need to use a cascade, so multi-stage PA. Okay, one stage the gain is not enough, so you put one stage, another stage to put them together, and then deliver the output. What I want to show you here is that if you keep the technology work at 1.2 volt supply, the saturated power is at this one. You can increase the supply to 1.8 volt. You push the saturated power by around 1 or 2 dB. This is critical for power amp. Okay, 1 or 2 dB is already critical. But why you can do this? You must have a safe operating area. That when I show you that, how can we keep this region? Look at the figure here. This is the VGS for M4. This is the VDS of M4. So if you focus on this M4 guy, normally this one eat most of the voltage happen. VDS and VGS, you make a side input, the voltage relationship between them will look like a circle. They will repeat here. If you have 1.2 volt, the region is here. You can see the limit is 0 to 1, and less than 1, or this is less than 1, more or less 1. You can keep them inside this circle. We call the safe operating area. Okay? They will keep like a circle. This is test under side wave. Okay? For another device, M3, more or less the same. 1.2 here. But 1.8, you can still keep here. As long as this is not over the limit, you're free to elevate the supply more. Okay? As less you decide this, okay? 1.2 volt, 1.8, still okay. 1.2, 1.8, still okay. So you are able to boost the power, even you are just using thin-oxide device. But the main issue is you need to ensure your safe operating area is handled by you at the beginning of the design. If this can be handled, why not increase this more? You increase the supply, you increase the output power, you achieve better performance, or the efficiency go higher. Okay, so just so simple for millimeter wave. This is a very important example. Okay, I show you this is a many kind of circuit. It's a mixed-VDD light driver. It's also a switch capacitor power amplifier. It's also a cascade power amplifier. Why I say so? Look at this free paper. From back to 2007, reported by them is a light driver, and University of Washington put this circuit as a PA, and Intel put this circuit as a cascade amplifier. The circuit structure is exactly the same for this free paper, but operate at different frequency. Perhaps this one is for low frequency. This one is for 2.4 gigahertz or 2 gigahertz. I don't remember exactly. But the concept is from these old technologies to very advanced 32 nanometer, this circuit help, really help. You have a cascade device here. Here, you put this as a bias, as a 1 VDD. I'll show you why. This is a very convenient bias. And then here, you put the clock here using a series of inverter. You power up this one, you can get another high voltage from between 0 and 2 VDD. Okay, you can consider this circuit as a power inverter. Inverter is a 0 to 1, 1 to 0, right? This is just a, if you give 0, you get a minus, you can get high VDD. So they are just like an inverter, but it's a power inverter from low voltage to high voltage, from small current to high current, depends on your design. So this can be a very powerful PA because what? You do not put any capacitor, right? You benefit fully from the speed of the technologies. If you find that this is the output that you can use, if you look at this paper for switch capacitor PA, you put a capacitor here. This can be an independent cell. You put a capacitor, you can charge the capacitor whenever you need. And then you put a lot of them, this becomes a power amplifier. Okay, this is an important concept. And for this paper, three of the design are quite successful. So you can see that they are published in important journal and conference. They make this circuit powerful from the past and to very high frequency. How it works, and I can show you this here. This is two possibilities for the output. One is a 2 volt, just reach to the limit. And another possibility is this load go down to the 0. And in between, how can you ensure load device is overdrive? As I showed you here, as I showed you before, if this is a 2 volt, you share by these two transistors, this will be 1 volt. Okay? How can you guarantee this will not overdrive? You put this at 1 volt. Okay. For this one, similarly, if you have 2 volt, and this is 2 volt, in between will be 2 volt, then you keep this one at 1 volt, the transistor will be safe. Okay? And you consider this at the low level. If this is the ground, this will be 1, this will be 2. You keep this as 2 and 1. You keep this part, okay. If this is 0, this is also 0. You keep this, this will be 0. You can keep this as 1, 1 will be fine, okay? Low transistor is more than 1 VDD at any time. And then you can see the beauty is that this is 1 VDD, 1, 1, 1. So it doesn't change in both cases. This one and this one, this one, this one will not change. So you can keep them together as 1 volt VDD. Just like I showed you in the previous slide. That's why this one is always connected to 1 volt VDD. This is the simplicity of this circuit. If you have just 2 top and 2 bottom, the simplicity is that the cascode device is just a 1 volt VDD. And then you can keep this in both output. These two keep everything safe, okay? But of course, if you look at this offer, he written a book on this large wafer. You put more transistor, of course you can increase the swing and increase the VDD, but the bias here will be very complicated. More than 2 will be complicated. Okay, if you just put 2, the bias is just simple, extremely simple. Okay, so you can keep them work. And another one just is what I should show you that guy. You work at Class D amplifier with a 10 volt output, 10 volt at 0.18 micron. So it's very unusual. How can they do this? They took a lot of device to put in cascode. Put the output stage very robust by using number of transistor. But in between the bias is quite complicated. Okay? And this is not easy for high frequency. So that's why this guy can do this. Why need to put 10 volt? Because if you design Class D amplifier, higher output voltage means more output current. You increase the efficiency, okay? Power is V multiplied by I. But whenever you put I more, you lost in the connections, okay? Normally, power M is efficient. If you put a high voltage, small current, it's better, okay? How can we do this? They integrate actually a DC-DC converter inside the chip to generate a 10 volt from a 3.3 volt. That means if you have the chip, you just keep 3.3, you internally generate 10 volt for you to power up this Class D amplifier, okay? This can be, this offer have a company, I think he is putting this in as a product, okay? You put 3.3, you develop a high performance Class D amplifier for the customer. Of course, 10 volt is not easy. You also need to design complicated ESD protections. Okay, if you have interest, you should look at this paper just report this year. And one more example is this one. It's also a custody amplifier, but at millimeter wave. The idea is you need keep this input circuit, okay? The front end at 1.1 volt is fast enough for millimeter wave. But how about the output? You need to be very powerful guy. So you need to maintain a 6.6 volt. And just like previous example, you need a number of cascode device. For example, this one, 3 transistor. And then you apply the custody on off at the top and the bottom. You put a resistor change, okay, to bias them. Okay, pay attention, here is them. This one is for high switching, so it's the voltage mode circuit. You use the voltage mode bias, okay? This is not robust, this is not current Muller, okay? Just a resistor ladder. Everything is biased in terms of voltage. They do not have a current Muller relationship, okay? Why? Because you only interest on a 0 and 1 at the output. So it's the voltage mode circuit. You do not care too much about small signal. Then you can free to use voltage bias more than current mode bias. Okay, traditionally people like current Muller, but this is not so useful for high voltage circuit. So you put a resistor ladder just to bias all the gates. Okay, in between, of course, this is the dynamic operations. If this one switch from 0 high to low, you also need to add some capacitor to compensate the dynamic voltage. If the dynamic voltage more than the reliability limit of the transistor, you still have the problem. The static is okay. Static, you can do the 1 DC simulation, you can check. But for dynamic, you need to run the signal, really apply the signal, and then see the swing internally. If there's something wrong due to this capacitor, you can add a capacitor to make this as a capacitor divider. You can also maintain the dynamic voltage smaller than the limit of the transistor. This is also one way. So whenever you do the design, static condition, surely you need to ensure that no problem. In dynamic condition, you still need to run the chip and time domain with full power and then see which node is really overdrive or not. If not possible, you need to add some compensation or you need to find another solutions. Okay? Of course, this is can be time consuming for big circuit, but normally only a small part of the circuit for a system is really need such a high voltage and really demand a high power. Then you just apply that kind of a high voltage technique, particular to this circuit, will be easier for a team or for a designer. Okay. I think we can have the break now, and then we can come back for the another half. I hope you still have your concentration. Thank you.